Hello, welcome to the seventh live session of Ponzi Topology 1 and Pre-Record. This is Shovik and what we discuss the matrix. Before starting today's session, let me know do you have any questions or any doubts from previous session or anything for assignment? Do you have any question or doubts? Please let me know.
Hello, sir.
Mustaq, tell me.
Yes. Hello.
Yeah, Mustaq, tell me.
Can you repeat the connectedness definition?
Sorry, I did not get the question. Can you please repeat again?
Can you repeat the connectedness definition?
Yeah, sure. Before starting, let me know, am I audible properly and is the
Yes,
screen
yes, you are
visible to you?
audible, both visible.
Okay, thanks for the confirmation. Okay,
Another
so
question with another that
yeah,
are with lower limit topology,
okay,
why
let me
it
write
is not metrizable?
it down. R with lower limit topology. Why not metrizable?
At first, before this question, you have please repeat the connectedness definition.
Okay, so so the definition connectedness goes as follows. So let X be a space. Okay, then X is said to be connected. Yeah, X said to be connected if X does not have any non-empty subset, non-empty subset, both open and closed. So, what does this mean? This means that a space is said to be connected if X has any set which is both open and closed, that will be either whole of X or that will be empty. That is to say, that is if X has any subset, if X has some subset G such that G is both open and closed, then G is equal to either X or empty. Okay. So this is what by mean connectedness. So this is one definition, and equivalently we can say the following. That is X does not have any separation. That is if X equal to U union V or U V non-empty and U intersection V empty and U V both open and closed in X, such a situation is not possible. Okay, this is by what we mean by connectedness. Okay, so this is the definition of connectedness. Understand, Mr. Mr. Do you
Yes,
understand?
yes. You can go to the next
Yeah,
question.
yeah. What's the next question? So next question was to show that R with lower limit
R with lower limit topology is not matrixable.
Okay, okay. So now R with lower limit topology, not metrized. How to do that? Okay. Uh, so look, firstly, observe that we have already seen. We have already seen that R with lower limit topology is mm, Lindelof. We have already seen that last class. Okay. Lindelof means what? That is every open cover has countable subcode. That is open cover as countable subcover. Okay. So now if R suffix L is metrizable, then being Lindelof, RL has to be second countable. Last class. So what this tells? So last session we have done one theorem, or we can tell it as exercise, that if a space is Lindelof or separable, and if it's metrizable, then it will be second countable. Okay. So this tells that if since R is Lindelof and if R is metrizable, then R will be second countable. Okay. But we have seen that R is not second countable in the last session. R cannot be second countable. We have seen it in the last session. So this tells that R with lower limit topology, not second, not metrizable. Okay. Do you understand?
Yes, yes.
Okay, thank you. Okay. So now, okay, do you have any more questions? Mr. Shimaze, do you have any question?
What about R? R is what about R connectedness? R only R.
Okay, you mean the
The R is connected.
real and visual topology, you mean that, right?
Real line
Okay.
is connected or not.
Well, the thing is, yeah, sorry, R that is with usual topology is connected. Sorry, R with usual topology is connected. Well, this proof is basically here. What we need to show here, basically, we need to show R does not have any set which is both open and closed. Okay, so this is what we need to. R does not have any set which is both open and closed. So this is what we need to prove. But this proof is basically This proof is especially part of real analysis. Okay. So for that you can look any textbook of real analysis. Okay, understand? So R with lower limit topology is connected,
Yes.
and the proof is actually part of real analysis. So I'm not going to the proof here. Okay. Now can you please think about that whether R with lower limit topology connected or not? Can you please think about? Please take your time. Let me know. R with lower limit topology is connected or not? Please let me know whether R with lower limit topology is connected or not. So what we need to show? You need to show that first of all, first you need to decide whether it will be connected or not. Then only you can give any kind of argument or answer.
No, RL is not connected.
Okay. Why?
The sets actually will take zero close to infinitive and minus infinitive to zero are both open in RL. Also, we can write the open set A close B open can be written as A close C open union C closed B open for C
Now
between A and B.
can you please repeat the argument? Let me write it down also what you're saying.
Any open set A close B open
Yes.
can be written as A
Yes.
close C open
Yes.
union
Yes.
C close B open
Yes. Okay.
C between A and B.
Yes. Correct.
So all open set can be decomposed into non-empty disjoint open set.
That's okay, but it does not tells you that. I mean, what you need to do? You need to show that any open set. I mean, you need to show R to the power L either sorry R suffix L either have any set which is both open and closed, or you need to show that if any set is both open and closed, that will be a whole space of or empty set, right? But this
Yeah.
opposite decomposition is nothing, right? Correct. Try to think about it. Take your time. Let me know. Okay, so the argument goes as follows. So look, you can write r suffix l as minus infinity open 0. Sorry, let me write it again. Minus infinity. Oh, what happened? Minus infinity open 0 union third bracket 0 comma open infinity. And this thing minus infinity comma 0, this can be written as union of x less than 0 x comma 0, right? And this is 0 comma infinity can be written as union of 0 comma y greater than 0, correct? Right? So this tells 1 Now, so this tells what? This tells that this thing is open and this thing is also open. And of course, the intersection is empty. So this implies what? Our lower limit topology admits a separation. Correct? So yeah, so that is a contradiction. I mean, so point is, I mean, it is nothing to contradict. The point is that our lower limit topology is not connected. So that is the thing. Okay. So yeah, so these are the things. So are you understanding my point? Did you
Yes,
understand the point?
yes.
So now, yes. Okay. Now there is one theorem which goes as follows. In the meantime, if you have any question or doubt, please let me know. You can stop and please ask because this session is mostly for problem solving sessions. Okay. So this theorem goes as follows. So suppose if y is subset of x and a separation, sorry. So statement goes as follows. If a set C and D forms a separation of x and if y is connected subsets of x, then y lies entirely within either C or D. So there is a statement. So what does this tells? It tells that uh, it- huh. so this tells that suppose this is uh, okay, 1 minute. Suppose this is suppose this is C and this is D, the whole is X. Okay. And now why the connectors are space? So the question is that, so point is that such a thing, if it is Y, such a situation not possible. Okay. Such a situation is not possible. This is what it needs to be proved. Okay. So please think about it and let me know the argument. Please take your time. I shall be back in a few minutes. So, are you able to solve it? Or do you have any idea how to approach the problem? So, what you need to do? You need to do the um, so you need to show that such a situation not possible. That is, either y lies in x. That is, we need to show either y lies in c or y lies in it. Right? This is what is need to be shown. Correct? Okay. So, what will we will start a contradiction. So we assume let y intersection c non-empty and y intersection d non-empty, and we shall somehow try to do some kind of contradiction. Okay. Now it is given that c and d forms a separation of x. That is simple as what? C and in unit d is equal to x. C intersection d is equal to empty. C D both open in x. Okay. Now take intersection of y box. This is simple as what? C union D intersection y is equal to y. Okay. And this C union D intersection y is what? C intersection y union D intersection y. Okay. This C intersection y union D, this thing is what? This thing is open in y. In the intersection y, this will be open in y. So this implies that y can move, then y. So this implies what? So this tells that y admits a separation, right? This tells what? This tells y. So this tells that the y is disconnected. But that is not possible, right? So y has to be connected. So this implies y has to be connected. So that's the context. So this implies what? So this implies either y intersection C empty or y intersection D empty. This first thing implies y sub of D, and the second y intersection D implies y subset of C. So this is the thing. Okay. So yeah. So this is the argument. Please let me know that do you understand properly or not. Please let me know whether do you understand properly or not. Okay. Okay. Shumes. So okay. So the argument goes as follows. Okay. So look, 1 minute. Let me have some water. So, Sumesh, so look, so what we need to show? We need to show that suppose C and D forms a separation of Y is connected. We need to show Y cars either lie within C and D. Okay, this is what we need to show. That is that situation as in the picture not possible. Okay, for that, what do we assume? Suppose we assume that 1 minute. We assume that Y intersects both C and D. So suppose Y intersects C in ornament and Y intersects D in ornament. Okay. Now since C and D forms the separation of X, so C union D equal to X and C intersection D equal to empty, and C and D are open in X. Okay. So this implies C union D intersection Y is equal to Y. Correct. So this implies C intersection Y union D intersection Y. This is both open in Y. This one both open in Y. Okay. And this implies Y admits separation, and that implies Y is disconnected, which tells that Y has to be connected. So this tells what? This tells that either Y intersection C is equal to empty or Y intersection D is equal to empty. So either Y subset of D, C or Y subset of D. So this tells that um, that since Y is connected and if C and the separation of the bigger space, Y will lie entirely within C or within D. Okay. So this is the thing. Uh, this is the argument. Okay. So now let's go for the next thing. Okay. The next thing, the next is the following. Union of connected subsets of X having a common point. Sorry, having a common point is again connected. Connected subsets having a common but is again connected. How to do that? So think, try to, so look. So, so what to show actually mathematically? That is, let X alpha subset of X are connected and let X belongs to intersection X alpha. Now we need to show that union of X alpha is also connected. Okay. So please take your time, think about it, and let me know the argument. I shall be back in a few minutes. Okay. Well, are you able to figure out how to approach this problem? So one possible way is to do the method of contradiction, right? So for that, what you can do, you can okay. So you need to show disconnected. So you assume that it's disconnected. Suppose I assume that union of x is disconnected. That is. So assume uh, union x alpha disconnected. That is union x alpha is equal to C union D, where C, D are open in union x alpha, their intersection empty, and C, D both are non-empty. Okay. Now try to figure some contradiction. Okay. Try to figure out some contradiction. Take your time. Hello, Sham. Hello. Hello, Sam. Hello. Are you able to hear me? Okay. It might be there was an network issue on your side. So, 1 minute, please. Okay. So, the question is as the follows. So, question is you need to show the union of characters also X having a common point is connected. Okay. So, basically, mathematical one need to show is the following. That suppose X alpha are the collection of connected subspace and let X belongs to intersection X alpha. We need to show union X alpha is also connected. Okay. So for that, we need to use the method of contradiction. And suppose we are assuming the union of X alpha disconnected. Okay. That is, we are assuming the union alpha X alpha equals C union D, or C or D are open in union of X alpha, where C D C intersection DMD and C and D not empty. Okay. Now you try use this and try to somehow come up with some contradiction. Okay. Think about it and let me know. Okay. Okay. It seems that it is taking more than time than expected. So let me write the solution for you. Okay, so let me explain. Okay. So, so this union of X alpha is with this. Okay. Now choose alpha naught belongs to that collection alpha. Okay. So this implies X alpha naught subset of C union D. Note that X alpha naught is given to be connected. So this implies that X alpha naught subset of C or X alpha naught subset of D. Okay. Now assume X alpha naught subset of C. Okay. Now if this is true, you will claim that X alpha subset of C for all alpha. How? Let's assume let's X beta subset of D for some beta. So these implies X alpha naught intersection X beta subset of C intersection D, which is empty. These implies this intersection X alpha is empty. That is a contradiction, right? So this implies that X beta subset of C also. So this implies that X alpha subset of C for all alpha, correct? So this tells what? This tells X alpha subset of C, and this implies what? Union of X alpha also subset of D. But we have initially checked that union of X alpha is equal to C union D. So this implies what? D is empty set, right? So that is the contradiction. So that is the contradiction, right? Hence, union of X alpha is connected. So this is the full argument. Please take your time and go through the argument once. So let me know whether everything is clear to you or not. Well, so let me re-explain this. So 1 minute, please. Yeah. So what we have, so suppose we assume, so okay, so we have assumed that okay, so we are assumed that union of x are disconnected. Okay, so that is union of x alpha equal to c union D. Okay, c and d are open and union of x alpha, or c intersection d empty, or c intersection non empty. Okay. What we need to show, we need to find out some contradiction, because we need to show union of x alpha is connected. Okay, so since we're trying to find a contradiction, so we assume that is disconnected, that's the union of x alpha is equal to c union D. Okay. So now, so we are choosing some alpha naught from alpha. So x alpha naught subset of C union D, and x alpha naught is connected. So this implies x alpha naught subset of C, or x alpha naught subset of D. Okay. Now, assume that x alpha naught subset of C. Now we are trying to show that x alpha subset of C. Okay. For all alpha, this is what we are trying to do. Okay. Suppose x beta subset of B for some beta, because either x beta subset of C or x beta subset of D. Okay. So we are trying to show it is the only possibility. Okay. So, uh, hmm. But if this is the case, this tells x alpha so intersection x beta subset of C intersection which is empty. This tells the intersection x alpha equal empty. So that is a contradiction. So our assumption is wrong. So this tells that union that x beta subset of C also. This tells that union of this tells x alpha intersection sub of C for all alpha also. Now this tells the union of x alpha subset of C. Okay, that the union of x alpha equals C union D, and D equal to empty. So this tells that union of x alpha is also connected. So that is the contradiction. Okay. So this is an empty connector. So that's the union of x alpha is also connected. Okay. Please go through document one and let me know do you have any question or any doubt, or else, uh, I shall go for the next question. Please let me know do you have any doubt or any question, or else I shall go for the next question. Oh, well. So I hope this argument is clear to everybody. Now, let's. Oh, thanks, Shumes. Yeah, okay, okay. So now let's go for the next question. So the statement goes as follows. I mean, this thing I have, this statement I'm not going to prove, just I am writing the statement. The statement connected. Okay. The continuous image. Of connected space. The continuous image of connected space is connected. Okay. So how to prove that? So I mean, just please take your time and think about. This is very easy. I'm not going to. A second one also. Finite Cartesian product. That is if x and y connected. This implies x cross y connected. Now, for this question, think about it and try to do but yourself first. Okay, please take your time. So, so x cross y connected. Okay, now try to write x cross y as union of some connected subspaces. Okay, please think about it. Try to sorry, try to visualize it graphically at least that how that x cross y might look like and how you can write x cross y is equal to union of u alpha. How you can find this such a u alpha also. Okay, think about it now. Let me know. Well, so yeah, so it's very complicated. It's at least a little complicated. So let me explain it. Okay. So choose some x comma y. Okay. So this is y and this is x. Okay. Now consider tx. This is equal to singleton x cross y, and consider ty. This is equal to x cross singleton y. Okay. This tx is connected. This ty also connected. Y as x connected, and these two are connected as y connected. Okay. Okay. This implies, so now this is tx and ty. Okay. And tx intersection ty, this is equal to xy. So this implies tx union ty connected. Okay. This union is also connected. Okay. Now what we are doing is the following. So we shall do that. One minute, please. So now, so fix an x naught, fix an y naught. So I fix it. Okay. So this implies what? This implies tx union ty not connect. Okay. So suppose this is y naught and fix this. Okay. Now if you vary x, okay. So we are now varying x. Okay. So now union of tx union ty not also connected. Y as intersection has common point. Okay. So this is the thing. You understand? So this tells what? This tells that x cross y is also connected. Okay. So, so this is the full argument telling that x can y x was y connected. So let me repeat it down. So first of all, what we target? Target is to x cross y should be written as union of u alpha and u alpha is connected. This u alpha has to find out, right? So for that, what we have done, we have chosen this to be x u alpha and this chosen to be dy tx. Okay, these are connected. They are union also connected. Okay, now we fix this line and a varying and we are varying x. Then union of x belongs to x. This is also connected. Okay. And since this intersection has a component, this tells that x cross y is also connected. So we are done. Okay. So that is the argument. Please think about it. Let me know whether are you able to understand or not. Okay. 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 Thanks, Shumes. So now let's go for next problem. 1 minute, everything working. Let me check. Okay, everything working fine. Now let's go for the next problem. Uh, okay. So next problem is as follows. Let n be a sequence of connected sets of x such that xn intersection xn plus 1. Sorry, that should be A intersection n plus 1 non-empty. Okay, for all n. So that union of A n is connected. So yeah. So try to think about it. So what do you need to do? So you need to you need to start with the contradiction. You start with that union A n disconnect and derive contradiction. Okay, think about it. So take your time. Let me know how you are deriving contradiction. Okay. Okay, so now, so, hmm, well, it seems that you. Okay, so let me explain. It's the same way as the previous intersection problem. So, let union of A n is equal to C union D. Okay, the separation. Okay, now suppose A n one subset of C un. Sorry, this thing is anyway subset of C union D. Correct, and this A n one is connected. So this implies A n not subset of C or A not subset of D. Okay, let A not subset of C. Then we're claiming that claim is that A not so claim is that A subset of C for all. Okay. Now proof of claim. Proof of claim. So suppose let AM subset of D for some M. Okay. So this implies that AN intersection AM empty. So that is a contradiction, right? So this tells that AM subset of D. So this tells that AN subset of C for all N. This tells that union AN subset of C. But this union of AN, this is equal to C union D. So this implies what? D is empty. So that is the contradiction. Okay. So So the D is equal to empty, so it's a contradiction. Okay. So so this is the argument. So yeah, this is almost the same argument as the previous. So there is, I hope this argument is clear to everybody. In case you have any problem, please um, ask me. Okay. Now the next question. Now let X alpha be a collection of connected subspace of X, and let A be a connected subspace of X. Show that oh, A intersection A alpha, if non-empty for all alpha, then A union of union A alpha is connected. Try to show this. So what does this mean? So obviously, so let me, so diagrammatically, so this is A and these are all A alphas. So now obviously that now try to show this union is connected. Okay, try to show this. I mean, you can here use again the same argument. Let's suppose the unit is connected, but no need to do this. I think whatever we have proved till now that can be used directly and proved. Okay, so please take your time. Please let me know. Well, so let me explain this. So, well, it was not that much hard, but one minute, please. It was not that much hard, but you should solve it by yourself. Anyway, let's try to solve it. Okay. So this A union of this thing can be written as union of alpha A union alpha, right? Now since now A intersection A alpha non-empty, this implies A union A alpha connected. For alpha, this implies union of alpha A union A alpha connected. This implies A union of union alpha A alpha connected. Okay. So A union A alpha is connected. So that is the argument. Okay. So there is nothing to do complicated. Why this union connected? Because intersection alpha A intersection A alpha non-empty. That's why this implies that A union of sorry A alpha is connected. Okay. So that is the full argument. Okay. Hmm. So now, so yeah, so there is nothing thing really actually you have done except the fact that we have used some previous arguments. Okay. Okay. Now, okay. Now the next problem is as follows. Okay. So the next question is as follows. So let A subset of X, B subset of Y, and X and Y are connected. Then show that X cross Y minus a cross b. Yeah, show that x cross y minus a cross b is connected. How to prove? So for this, you need to consider diagram, okay, and try to figure out that why such a situation holds, okay. So this is x. So this is the picture of the situation. Now try to understand this. So try to think about how to approach the problem. I mean, the argument is quite easy, but you first try to think about. Let's think about it. Let me know. Okay, Shumis. Okay. So, look. So we have already given A and B are some source when X and Y are connected. We need to show X cross Y minus A cross B is open. Okay. Sorry, X cross Y minus A cross connected. Okay. So what is one possible way? I mean, this is we need to show this thing is connected. Okay. So look, directly it is not possible to do something connected. So for that, what you need to do is the following: choose some point x cross y outside that space, okay, and consider this thing, consider this line, okay, tx union ty. This is connected. Okay. Okay. Now tx union ty not y not fixed. This is connected. This tx union ty not how to do. This will give this type of situations. Okay. And tx naught union x naught comma y naught does not belongs to a comma b. Okay. Tx naught union ty, this is also connected. Okay, these give the horizontal bars. Now union of x belongs to x minus a t x union ty naught, union of y belongs to the union of ty naught, union of tx naught, union ty connected. So so this is the argument. Okay. So in this way you can solve this problem. Okay. So okay. So that is the way. So this says that if x cross y minus a cross b, that is also connected. So yeah, so that is the thing. So if you have any doubt or any question, you can ask me in the next session, or else we can leave the session. Okay. Okay. So you do have any question or doubt? Please let me know. Okay, no doubt. So okay, so I'm leaving the session. Thank you.